Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In the last lecture, we qualitatively discussed how, starting from the basic kinetic theory of a plasma, we can reach to the fluid theory. Okay, and first we described that for each species, for example the ions, the electrons, we can describe, or rather we can consider separate fluids. Okay, so then the plasma can be considered as a multi-fluid. Okay, it's a combination of an ionic fluid, it's electronic fluid, and if the plasma is very weakly ionized, then neutral fluids. Okay, the neutral fluid that will also come into play. Now we also said that finally that if we are interested beyond a certain scale, both in length and both in space and time, then simply the total the quasi neutrality, okay, the charge quasi neutrality, okay, that is actually satisfied almost at each point of the flow field. Okay, so very locally, and then we can describe the plasma as just one single fluid. Okay, which is neither the pure ionic fluid nor the pure electronic fluid, but it's a combination of the two fluids. Okay, and this is known as popularly the monofluid model of plasma, or magnetohydrodynamics, which is also sometimes called with its abbreviation MHD. Okay, so in today's discussion we will mostly be trying to throw some light on different interesting properties of such MHD fluids. So as we discussed last time, that MHD is a monofluid theory of plasma, and it is valid only when we are interested beyond a certain length scale called the ion inertial length. Okay, of course in terms of time scale you can also estimate some time corresponding to that. So but to be very honest, it is so roughly speaking, if we are interested in the time scales much greater than the inverse of the ion or electronic gyro frequency, or the ion or electronic how to say that the cyclotronic, the gyro frequency, or the reciprocal of the ion or cyclotronic plasma frequency, then we are, most of the cases, it is already almost guaranteed that we are in the MHD region. Okay, so roughly what happens in the MHD region is that we are in such a long or large length scale or time scale that even for our time scales or length scales, the ions are moving considerably. Okay, and electrons are enslaved by the ion flow, as we described last time, that if we simply with an enormous amount of patience, if we study the movements of the clock's hands, then it is true that it is possible to even see that the hour's hand is also moving. But most of the cases, most often what happens that we don't have enough patience, so we can only see the seconds hand and sometimes minutes hand, but hours hand to move we really have to wait for long time. Okay, and if we have this level of patience here analogically, then ions are also found to move, and when ions are moved, electrons just make a background. Okay, and it simply follows the ions. So for an MHD fluid, as we discussed, that the inertia of the fluid is mainly governed by the ions. Okay, and that's why for an MHD fluid, the fluid velocity is almost equal to the ion fluid velocity. That was also evident from the formula. Okay, so of the monofluid velocity, which is nothing but a velocity of the center of mass of the two fluids, electronic fluids and ionic fluids. Okay, so here when we are just talking this monofluid model, for the simplicity we simply consider that our plasma is almost perfectly ionized, and which is the case when when this monofluid model actually comes to be appropriate, and then you have ions and electrons, so the number of neutral atoms are negligibly small. Okay, so the V, which is the MHD fluid velocity, will be simply very close to the ionic fluid velocity. But the current, on the other hand, which is given by J, is nothing but is equal to N times E. N is the common charge density, number density of both electrons and ions, times E. Okay, E is the electronic charge, times Vi minus V, that we also saw last time. Okay, so if we have this, then you can easily see that in this case, so whereas for this case, if you remember that simply V was Mi Vi plus Me Ve by Mi plus Me, and you can simply say that my Mi is, you can just simply divide everything by saying that your V is equal to Vi plus Me by Mi Ve by 1 plus Me by Mi. Okay, now since Me by Mi is negligibly small, and we consider that both Vi and Ve are of roughly of the same order, then we can neglect the whole thing, okay, with respect to Vi, and also we can neglect this factor in front of 1, and that's why we finally have V almost equal to Vi. Okay, now for the current, this is no longer true. This type of neglecting the electronic contribution does not work here. Okay, and we have to take the contribution of both these velocities. Okay, now if you remember the four equations, governing equations of magnetohydrodynamics, as we said, they are simply the continuity equation del rho del T plus divergence of rho V is equal to 0. Second is the momentum evolution equation, or here just I have written in terms of accelerations. So del V del T plus V dot nabla V is equal to minus nabla P by rho plus J cross B by rho minus gradient of phi, which is the conservative, represents the conservative body force, plus the viscous term nu times nabla square B. Okay, and this is the induction equation. Okay, this is the induction equation, which is nothing but del V del T is equal to curl of V cross B plus eta nabla square B. So this term comes from the if you remember from the generalized Ohm's law, and this is something analogous to the dissipation term for the magnetic fields. Okay, and it is called the magnetic diffusivity. And finally we have to close the equation, and since we are just, again for the sake of simplicity, we are not considering the energy equation, we simply close the equation at this level just by saying that our fluid is polytropic. Okay, even simpler than saying it to be barotropic. So this is a simpler version of barotropic, where P has this specific form K times rho to the power gamma. Okay, of course once again gamma can be anything real quantity, but gamma can be positive, negative. Okay, but and so this is just writing this form does not guarantee that the system is adiabatic. Okay, this is a general polytropic system. This rho gamma can be equal to -2, for example. That is also possible. Okay, so with these equations we can start studying the features or different properties of MHD equations. Okay, now just before that, let me just point out one thing, that where this magnetic diffusivity term, okay, that term with eta, and the fluid viscosity term, they are negligible. Okay, then I mean simply this eta nabla square v and nu nabla square v or Laplacian v and this eta times Laplacian b, they can be dropped or they can be ignored, and we then talk of the regime which is known as ideal magnetohydrodynamics. And the good news is that in most of the cases of astrophysics and of course there are strong exceptions, but in most cases of astrophysics and space physics, a large number of phenomena can be explained just by using ideal MHD. Why that I will be coming in some next, during some next discussion. Okay, so one specific feature of MHD equation is the type of Lorentz force in the force equation. So that equation is absent in general for neutral fluids. So neutral fluids are not charged, so they don't have this Lorentz force in the force equation. So Lorentz force is nothing but J cross B by rho. So J is simply equal to N times E Vi minus Ve. But again, if you remember Maxwell Ampere's law, what is J? So J can also be written as curl of B is equal to mu naught J, okay, plus mu 0 epsilon 0 del E del T. Now this is called the displacement term, and this term actually can be neglected with respect to this term. Okay, this is neglected. Okay, you can show by order analysis if the plasma is non-relativistic in nature. Okay, and we are considering here non-relativistic plasmas. Okay, so for our case, curl of B is simply equal to mu naught J. Okay, so then we can write simply J as 1 by mu 0 curl of B. So this total thing comes then 1 by mu 0 rho curl of B cross B, and if you know this special vector identity, this is nothing but minus gradient of B square by 2 plus B dot nabla B. Okay, you see sometimes we will see in a short while that will be very important to understand two different aspects of Lorentz force. Now sometimes we say that, okay, why this is really useful to remember the vector identities or to have a good grip over the vector identities both in vector algebra and vector calculus. The reason is that if you just retain your term in this expression, you don't understand what is the physical significance, but once you write in this expression, you can actually see the effects are prominent then, okay, in this writing. Okay, so that's why it is always good to have a good grip over the different type of vector identities, and it is good to make a habit to write different expressions using write in equivalent expressions using vector identities like we are doing here. Okay, so once I write in this form the whole thing, you now see that, so I have mu 0 rho times minus gradient of B square by 2 plus B dot nabla B. Now mu 0 can be taken inside, so it will be minus gradient of this B square by 2 mu 0 by rho. And what does that look like? It simply looks that this b square by 2 mu 0 is behaving like a pressure type of quantity, which we call sometimes the magnetic pressure. Okay, in several literature you can see this is nothing but b square by 2 mu 0, this is nothing but pm, they use this symbol. I am using here just p due to b. Okay, so this is a pressure term. Okay, so and what happens then in the total equation, you will then have two terms, one is like this and another will be like this, 2 mu 0, and which is nothing but pb. So the total pressure will be p plus pb. It's an effective pressure. Okay, so you see that this writing style gives us several several significance of this whole expression. So this one is like a pressure and we write this, and this one, what is this? This one is known as tension, and why this is known as magnetic tension, that we will be coming in a few minutes. But before that, now let us try to understand that in MHD equation we have two contributions from pressure type of thing. Of course, there one contribution can be coming, which is can come if we write this advective term in terms of this and v cross omega, which we wrote in term in the case where we were studying the effect of rotation. Here we will not write that simply because we know what is the meaning of this v dot nabla v, and to be very honest, we have reduced this term because in the equation we did not have any other terms like this, but v dot nabla v has a term which is identical to this, and that is v dot nabla v. So we don't have to rewrite v dot nabla v in terms of gradient v square by 2 and v cross omega. Okay, that we don't need. So in an MHD plasma, the pressure consists mainly of two type of terms. One is P, the normal pressure, another is B square by 2 mu 0. One simple point to make here, this B square by 2 mu 0 is also equal to the magnetic energy density, okay, in an electromagnetic field, if you remember. Anyways, so these two things now can act together on the MHD fluid, and one can be greater than the other, one can be less than the other. They can have different type of interplay, okay, according to the relative importance of one with respect to the other. And how to measure that? A quantitative measure of that is given by the so-called beta parameter of a plasma. So beta parameter is nothing but the ratio of P to B square by 2 mu 0. So P is in the numerator and B square by 2 mu 0 is at the denominator. So finally beta is nothing but P by B square by 2 mu 0. So this 2 mu 0 can come up. So it will be simply 2 mu 0 P by B square. Okay. Now we will see two specific cases. One is the isothermal case where gamma is equal to 1, and so P is simply proportional to the density. That case we have already encountered, okay, previously for a normal fluid. So this conclusion remains unchanged. So then isothermal fluid is nothing but P is equal to Cs square times rho, and beta is equal to 2 Cs square by B square, okay, where this small b is introduced deliberately, okay, and this one actually is of much importance for the physicists who work in space physics mostly, okay. So this b is a magnetic field normalized to a velocity. So just check that if b is divided by root over mu 0 rho, then it is just getting a dimension of a velocity, okay. So this one we just call as small b, and so our beta parameter will then simply be equal to 2Cs square by B square. Okay. Now, so now you can easily understand that if the temperature of the beta, of the plasma increases, then what happens? Cs square increases, so its beta value will increase. If on the other hand your system's the magnetic field is very strong, then beta value decreases. Okay. Now we consider another another simple case, which is the case of polytropic case. So gamma is equal to gamma polytropic, for example. So then the pressure is no longer just proportional to rho, but pressure can be written as Cs square rho by gamma, but this Cs square itself is a variable. Okay. Now this beta can be written as simply equal to, so just replacing the expression of P in this expression, we can write beta is equal to 2Cs square by gamma B square. Okay. And then you can easily see that both from these things we have the same conclusion, that whenever your Cs is very important, that means the system has a very high temperature, beta is high, and if B is weak, then also beta is high. Okay. But on the other hand, if B is strong, then beta is low. So from this we now make two limits. So beta tends to 0. What does it imply? So beta tends to 0 can imply two situations. Okay, either of the two or both together. That is, first of all, Cs is tends to 0. That means the temperature is very low for the plasma. So the plasma should be very cold. And also there is another possibility, is that B should be very large. Okay, infinitely large. So it simply said that the plasma is subjected to a very strong magnetic field. Okay, which is a combination of course of an external field plus the internal field. Okay, so the total resultant magnetic field is very strong, and this type of plasma is known as cold and magnetized plasma. Okay. So it is true that if the plasma is very cold, and even if the magnetic field is not very strong, simply then also it is good enough to have a beta value very close to 0. But if we have just two conditions together, which we call cold and magnetized plasma, then we must have beta tends to 0. Now on the other hand, the diametrically opposite case is the beta tending to infinity, and that is the case of where you can easily see from here when beta tends to infinity, when the temperature is very strong, very large. Okay, so beta tends to infinity for an isothermal plasma simply says that the plasma is very hot. Okay, but still the plasma is can be written in this isothermal, using this isothermal closure, because if you try to go into the detail, you can actually see that if a plasma is very hot, then in general there can be much more sophisticated closures. Okay. Whatever. Now for polytropic case, if beta is tending to infinity, it simply says that maybe just a minute. So it will simply tell you that this Cs, okay, is so yeah, there is a point to make actually. So in normal literatures, you can see that beta tends to infinity gives us the incompressible plasma. But just try to think. Okay, so Okay, so I mean the thing is that first of all, from this equation you can have this idea that maybe when beta tends to infinity, it simply makes CS square tending to infinity, and that gives us something nearly the incompressible medium. But this is a bit typical because this is not possible. This relation is only true for isothermal plasma. Okay, and from isothermal plasma it is not evident to go to the incompressible limit. On the other hand, from polytropic plasma one can go to the incompressible limit for gamma tends to tends to infinity, very large value. But the problem is that the beta is equal to 2c square by gamma b square. Okay, now it is true that cs square just it's exactly tending to infinity. Okay, and gamma is also tending to infinity, and actually cs square by gamma, which is p by rho, is something which is finite for an incompressible flow. Okay, and so to be very honest, in my opinion, it is a bit, so according to the literature, although I wrote here this incompressible thing, okay, maybe it is more appropriate just to say that it is a hot and weakly magnetized plasma. Okay, so incompressible at for the time being I write like this. Okay, okay, so but one thing is clear, that when beta is very large, then cs should be large and it should correspond to, irrespective of gamma, okay, a high temperature. Okay, and the same thing when when the magnetic field is weak, that means B is weaker, then it will also correspond a very high beta. Okay, now try to, okay, now coming to a very practical question, that so we know now beta value is important to know the nature of the plasma. Okay, so now try to calculate the plasma beta, assuming gamma almost equal to 5 by 3 for the solar wind at 1 astronomical unit. For that I suggest you to search on over internet the typical values of different type of physical quantities, so that you can calculate cs square. You have some idea about the magnetic field, okay, of solar wind at 1 astronomical unit, and then you calculate both for ions and electrons and check which one is larger. And finally the question is that for a plasma, what should be the combined or the resultant beta? Okay, how to do that? So think all these questions, and if you are blocked, you can write me over forum and we can discuss. Okay, thank you. Now coming to this question, so we have already discussed about the magnetic pressure part, but I introduced this part which looks like an advective term but in terms of the magnetic field only, and this is known as the magnetic tension. Why? So just consider this red curve is the it represents one line of force of the magnetic field. Okay, so it's a magnetic line of force. Now I am simply interested in this small segment, and within this small segment the tangential direction is along t, small t, and this segment I call as ds, and the curvature of this small part is given by this, the radius of curvature, this RC, and O is the center of curvature. Okay, now ds is nothing but, we all know, root over dx square plus dy square plus dz square, that is no surprise, and OM is the radius of curvature, this one. N is the unit vector which is acting radially inward from that line of force to the center of curvature. Okay, now I write B dot nabla B and try to analyze this. What is this? So this is nothing but the directional derivative of B, okay, in the direction of B itself, and this is again B ds, B times del S, because del S is the partial differentiation along this line of force. Okay, so S is, ds is simply the segment along this line of force. So B times del S, which will be now acting on B, and what is that B for this ds? This is the B, which is the magnitude, times T. This is the unit vector. Okay, so the magnetic field is at every point of a magnetic line of force, the corresponding magnetic field is just tangentially directed. That's the definition. So we write this in this form, and then we can write B, then this one we expand as del B del S T cap plus del T cap del S B. Of course, here the unit vector changes its direction with time. Okay, so that's why this term is non-zero, and this term is easy to analyze. So del S B square by 2 times T cap, because okay, you can simply write this in this form. And what about this term? This term, just using simple vector algebra, you can geometry, you can simply obtain, you can simply find that this term is given by 1 by RC times n cap. Okay, so if this is the case, then this is 1 by RC times n cap, then the whole thing will be B square by RC times n cap. So this one is the tension along B, because this is along the tangent direction. Okay, and this one we are calling tension perpendicular to B. Okay, so if, for example, the magnetic field intensity increases, okay, intensity increases, then this tension will be will be increasing, and thereby making a force, so that the the magnetic lines of force are well tied. Okay, just like a cord under a tension. And this one is much more interesting. In the case, if you can see that in the case you have some, the magnetic lines of force which are getting much more curved due to some additional matter or some increase in the magnetic field intensity. And when it is getting curved, let's say like this, then its radius of curvature decreases. Okay, so the radius of curvature now decreases. This is now RC prime. When radius of curvature decreases, this term increases. And then it simply says that when it has this type of geometry, then you have something of a net force which is acting in this direction. So that means whenever this tension, what does it do? Whenever this magnetic field gets deformed from its original position, it tries to bring it back to the original position. That's why it looks like, it behaves like a tension. Okay, so that was all about the tension part. Now coming to another interesting thing, which is the frozen in field theorem for MHD. So for ideal MHD, we all can now remember from the last discussion that the Faraday's law actually becomes del B del T is equal to curl of V cross B, because the eta nabla square B is dropped. And if we recall from our previous lectures, when we were talking about the different properties of ideal fluids, then we talked about the Kelvin vorticity theorem, and we said that any vector field, when it just satisfies something like, so any vector field A, if it satisfies an evolution equation like this, where V is the fluid velocity, okay, then this equation will have, then this quantity will have a flux which is, will have a, this quantity will have an associated flux which will simply be then A dot ds, this which will be conserved along any surface inside the fluid. And another way of writing this is d dt of this is equal to 0. Okay, so that's exactly what we have written over here, that here the field which is satisfying this equation, magic equation, is B, the magnetic field, and that's why d dt of the surface integral of B dot ds is equal to 0, where we are just talking about the surface, any surface, okay, made by the fluid elements, any surface which is made by the fluid elements and moves with the fluid. So of course, if it is made by the fluid elements, so it's a real surface which is containing the fluid elements. Okay, so what is the meaning of this? That, so of course this surface also changes its area with time. That's why I have written this S as an explicit time dependence. Now it simply says this is equal to 0 means that in ideal MHD the magnetic lines of force, they are frozen in the plasma or the matter. Okay, so that's why whenever you take any arbitrary area in a fluid and then you just trace this area from here, let's say now after some time it is coming here, or after some time let's say it goes there. Okay, in both cases if you just calculate B dot ds here, here or here, you will always have the same value, and that simply says that, because we are just following one surface made by the fluid elements, we are actually following a slice of matter. So if we are keeping our target intact, then the flux is also intact. So our target was just a slice of matter. So it simply says that the magnetic field is frozen with the matter or with the plasma. I have a small question for you. Can we also say that the same thing for A, where B is equal to curl of A? So just then you have to derive the evolution equation for A and check whether this satisfies this magic equation or not. Okay, this is typically very easy, and you will see that A does not obey this type or satisfy this type of equation. Okay, so before ending this discussion, let me just tell you some important notes. Okay, so divergence of B is always 0. So for a magnetic flux tube, if you just take a magnetic flux tube in an MHD fluid, then if you consider a volume, okay, of this, then the total magnetic flux through the whole surface which encloses that volume of the magnetic flux of tube also is 0. That is simply because of the Gauss's divergence theorem. So because you just have to do this d tau, and that will be simply equal to closed surface integral B dot nds is equal to 0. Now the flux, so the direction of the area of this lateral surface is always perpendicular, whereas the direction of the magnetic field at every point is the tangential. Okay, that's why the total flux vanishes at every point of the lateral surface. So this is only non-zero at this surface and this surface. So that's why the magnetic flux entering through the cross-sectional surface of a magnetic flux tube exactly is equal to the flux which is coming out of the opposite cross-sectional surface of that same tube. So magnetic flux across any cross-sectional surface of a magnetic flux tube is always constant. So this is very general statement. We don't need Kelvin vorticity theorem to be true for that. That means we don't need the magnetic field to satisfy the magic equation for that. It simply says that even if this is not true for some system, for example, if your system has some viscosity, then this is not true. There will be a term with viscosity, eta nabla square b. But still then this fact is correct, that the magnetic flux across any cross-sectional surface of a magnetic flux tube is constant. But which is not constant correct there is that if you take any arbitrary cross-section, any arbitrary surface made by the fluid element inside the flow field, then if you calculate the total flux, okay, across the surface of the magnetic field, then whether this will be the same to that surface which is evolved in time and now is situated to a new position. Okay, for that to be true, that means if you just start with a surface over here, you calculate b dot ds, okay, and then you take the integral over this surface. Then this surface with the fluid flow, for example, now comes here. Okay. Now you calculate again integration b dot ds. The question is whether this will be equal. Yes. For that to be equal, b has to satisfy this magic equation. Okay. So this is all about this Frozen-in theorem for the magnetic field and in ideal MHD. Okay, so in the next discussion I will start discussing about the inviscid invariance of MHD fluids. Okay, thank you very much.